Hello everybody. Today we'll be talking about vectors, in specific vector addition. This video is actually for the Set 5 students because you will not have encountered vectors. For the Set 4 Express students, be it combined science of pure, if you want a quick revision of what vector is, vector addition, then you can just watch this video as well. Alright, before we talk about vector diagrams, it is actually quite useful for us to talk a little bit about forces, because then it will help us frame our mindset and also allow us to use forces to in our discussion of vectors. It will make life a little bit easier for everybody. Alright, so just a quick refresher. What are forces? Forces is a push or pull. It must be exerted from one object onto another object, and the unit of the force is the Newton, symbolized with a big N. A force can slow down, speed up, stop. It can also change the direction of motion. Two classifications of forces: contact forces, which is forces that must touch, or two objects must touch for there to be contact forces, and non-contact forces, which are forces that act from a distance, things like gravity, electric force, and magnetic force. Alright, and before we begin, before we talk about vectors, it is also quite important for us to talk about, Alright, so before we carry on talking about vectors, it is useful for us to also talk about free body diagrams. How do we draw forces acting on a certain object? Because it helps us with our vector addition later on. So imagine I have an object being pushed to the left here, this object here. And then I tell you that the force is exerted by a person standing here, and he's pushing on the box in this way. Now, it is then quite natural for us to actually draw the force like this, because the guy is here, he's pushing on the box here, so it's in this direction. But in terms of our physics study, then actually this is not a correct way to represent the force. In physics, we represent the force acting on an object as originating from the object, meaning the arrow comes out, or the start of the arrow is from the object itself. So in this case, what you are drawing is that there's a force being felt on something that cannot be seen over here, and it's acting towards the left. If you want to draw a force acting on the box towards the left, then it should be drawn in this manner. Alright, so some examples of how we are going to draw free body diagrams. For example, I have a car in motion towards the right. I have indicated these are all the possible forces that are acting on this car. So remember some of the rules. The forces must originate from the object that the force is being felt on. So force of engine, since the car is moving towards the right, so the force of the engine must be towards the right. So again, I start from the car, I draw in the direction, I label the force. Now, in most cases, you should write force of engine. But in this case, I already labeled 1, 2, 3, 4 just for ease. The next one is weight. Weight originates from the center of gravity of the object. So from the center of the gravity of the object, I draw downwards, label the force. Number 3, friction. Friction, I would prefer it if all of you could draw the friction in between the two forces to represent friction. So for example, friction is generated between the car and the floor, so I draw it in between the two surfaces in the direction of the frictional force. So 3. Normal reaction force is the force of the floor on the car, so I draw it where it originates from, which is from the bottom of the car and upwards. 4. And finally, air resistance, just draw it like this. Alright, we go on into our study of vector diagrams, and we are only at the O level expected to draw or add two vectors using a graphical method. Of course, later on, if you go on to further your studies, there's actually a mathematical and more accurate way to do it, but it is sufficient at the O level to use only a graphical method. Alright, before we begin discussing about vectors, it is useful for us to refresh ourselves what a vector actually is. So scalar quantities are physical quantities that only have magnitude. Only have magnitude, magnitude meaning the size of the physical quantity. For example, speed. 10 is the magnitude of the speed. Meter per second is the unit. So if I want to indicate a bigger speed or larger speed, then the number should be bigger lah, 20 meter per second. Vector quantities, however, are physical quantities that have both magnitude and direction. So the most easiest for us to deal with now is force. When we say an object force of 5 Newton is felt, it is not sufficient to just say 5 Newton because you haven't told me the direction, right? Is it upwards? Is it to the right? Is it to the left? Is it downwards? Or even at an angle? You need to be able to tell me for you to give a full description of a force. Alright? When we add 5 meter cube of water to 5 meter cube of water, easy, the answer is 10 meter cube, just 5 plus 5. Because they are scalars, we only just need to add them. But when we add a 5 Newton force to another 5 Newton force, is the answer still 10 Newtons, just like this? The answer is that is not always true, because the direction of the force plays a big part in what is your end result of the two forces. So this is what we are doing. We are trying to add 5 Newton force, one vector to another vector, and we are doing it using a graphical method. So before we even start on drawing or vector addition, it is useful for us to know how to draw a vector, just one vector. So let's say you are tasked to represent a force of 20 Newtons acting in a direction 45 degrees north of east, which means in this direction. Then first and foremost, you need to tell me how you're going to show 20 Newtons on paper, the magnitude of 20 Newtons on paper. If they ask you to draw length, then it's quite easy lah. You just measure 1 cm, then you tell me it's 1 cm drawn full to scale. But how do you represent 20 Newton? How does a person know how much is equivalent to 20 Newton? So you need to define a scale first before you do anything. So use a scale. 1 cm is to 5 Newtons to tell the person reading the diagram or looking at the diagram how much is 20 Newtons. Then in a graphical method, you need to draw the direction accurately, which means you need to use this fella. Alright. And finally, how to draw? You draw here and with an arrow. Now, I know this is what is in your notes with a line and an arrowhead at the end, but for our purpose of O levels, can you draw the arrow in the center instead? Alright, later on you'll find out why it's better to put it in the center than at the end. Alright, so when we add two vectors together, we get a final vector, which is the resultant vector. Now, this all sounds very complicated, but the basic understanding is that the resultant vector produces the same effect as the individual vectors combined. So, you already know this from your study of Newton's laws. So, because in Newton's laws, they don't expect you to do fancy stuff like they just want you to calculate using parallel vectors. So, the easiest one that we have, or the most classic example, if I have a box with a 3 Newton force acting to the right and a 5 Newton force acting to the right, what is the resultant force? Then you know it is 8 Newtons, because the combined effect of the 3 Newton and 5 Newton towards the right must be 8 Newtons towards the right. So how to represent in a graphical way for vectors is I draw 3 Newtons acting towards the right, and then I draw another 5 Newtons, the line in red here, towards the right, which then gives me a combined effect of 8 Newtons drawn in this way. Now, the resultant vector is usually represented by a double-headed arrow. So, because you add two vectors together, you draw two arrowheads. Alright, let's just use another example. 3 Newtons to the left, 5 Newtons to the right. So, how do we draw it? First and foremost, graphically, we draw 5 Newtons acting to the right. Remember, I must be drawn to scale, so you must provide a scale first for the person to read. And then, in red, you will see what I do is I add 3 Newtons back towards the right, towards the left. So the resultant effect is just a 2 Newton force in this way, which I've drawn here lah. So it goes 5 Newtons this way, 3 Newtons back. So from here to the end is only 2 Newtons. So it's 2 Newtons to the right. Even here it's easier, 3 Newtons to the left, 3 Newtons to the right, you know resultant force is 0. So graphically what is drawn is 3 newtons goes to the right. I don't know whether you can see, but 3 newtons vector first drawn to the right, then another 3 newton vector drawn to the left back in this direction, which ends up back at the original spot, which means 0 newtons. Alright, now parallel vectors are easy. Now, what happens when the vectors you want to add are not parallel? Then how do we find the resultant vectors? Alright, the idea is that we use the parallelogram method. Alright, either the parallelogram method or the head to tail method. Essentially, they are both the same things lah. So I'll just go into a little bit of detail how it is that you're going to find or add two vectors together. Alright, here I have vectors already drawn. This app is from Colorado Fed. I will link it in the description if you want to play with it. All credits to them. So I got two vectors here acting on one object here, this dot here at the center. So how do I find out if they are at an angle? How do I find out what is the resultant force of these two vectors? Alright, so if I were to show you the sum or the combined effect of this, the idea is that I will take the vector and the tail end of the vector, I will meet with the head of the other vector, and then from the start to the end, that is the resultant vector. So I give you an example lah. Let's say you are given some information. A guy walks let me see, a guy walks 15 meters. Let's say this scale is in meters, 15 meters up to the north and 15 meters east. So the end effect is that he will end up here lah. So it doesn't matter whether he walks 15 meters north and then 15 meters east, or he walks 15 meters east of then 15 meters north. Alright, the idea is that I can take this vector and put it here, and I can tell you what is the combined effect of it. So the combined effect is over here. Now, this is the head to tail method. I put the tail end of one of the vectors to the head of the other vector. Now, what is the parallelogram method then? Since I said just now, it doesn't matter which vectors go first, whether it's go 15 meters north, then 15 meters east, I can actually also move these vectors to be second. I make the tail of this vector now to meet the head of this. Right, so now I also get the same. This is another head to tail. But if you do head to tail twice, i.e. you do this one, or you do this one and move this vector up to here, you form essentially a parallelogram. Now it's all just nice 90 degrees, 90 degrees, so it forms actually just a nice square lah. So, but if you change certain things, let's say I drag it up here and I drag it up here, I change the angles. Then if I were to draw this, drag this from here to here, and then also at the same time drag this from here to here, then actually I would form a parallelogram here. 1, 2, 3, 4. So if you can imagine that lah. So there are some advantages in using certain ways over in certain types of question. I'll explain that in detail in a little while. Alright, so the best way for us to try this is by using an example. So I have a question here. A frame picture is hanging on a nail. The picture is held up by two strings. Each is 25 newtons. What is the resultant force due to these two strings? And then they ask you to deduce the weight of the picture. Now, if I were to look at the picture here, can you tell me what are all the forces acting on the pictures? So the easiest one for us to, the two easiest one for us to point out is actually the 25 Newton from string 1 and string 2. So how do we represent it? Remember, vectors are quantities that has magnitude and direction, so the direction must matter. So this 40 degrees here is not for play. You must take note of and make sure that when you draw this vector, you represent it correctly. Make sure the angle is represented correctly using a protractor. Right? So if I were to draw a vector diagram, then I first must tell what is the scale. Then I must represent these forces correctly in the correct angle. Means I need to measure 40 degrees and then correct to scale. If I use a scale of 1 cm is to 1 Newton, then this line on paper should be 25 cm because it's 25 newtons. Now, what are all the other forces acting on the picture apart from here and here? Alright, there should be also the weight acting downwards, the weight of the picture itself. Now, oftentimes you realize that when I discussed the learning outcomes, I said that we only need to know how to add two vectors together. But now you tell me I got three vectors. Alright, so how do I deal with it? Alright, so just take note, when they say an object does not move, or an object is being held up, an object is stationary, then the resultant of these two forces must exactly equal to the third one. Only then this force and this force will cancel out. My resultant force is 0 newtons, then it does not move. So essentially, even though it's a 3-vector problem, if I can find the resultant of two of them, then I know that the magnitude of this resultant must be exactly equals to this one to cancel out, and the direction is that it must be exactly opposite or 180 degrees away from this fella. Right? So let's discuss how to draw this question, and I would like to first deal with the parallelogram method. Alright, so here I have a list of steps. It should be on the next page of your slides. Plus, I represented the diagram that is in the question for ease. Alright, 40 degrees, F1 and F2. F1 is 25 newtons, F2 is also 25 newtons. Alright, so I told you there were two methods, parallelogram and head to tail, but essentially they are the same. But you need to know when to use parallelogram, or when it is easier to use parallelogram. Alright, in some of the questions, they will already give you a diagram where the forces of the two vectors you need to add are like this. They already give you, and then they give you an angle of, let's say, 40 degrees. Alright, in this kind of situation, it is preferable for you to use parallelogram because tail and tail is meeting here. So you have to move the tail to meet the head of one of the fella anyway. So when it's already tail and tail meeting from one point, then it's preferable for us to just use the parallelogram method. So let's run through how we are going to deal with this. Remember, step 1, before you do anything, you need to tell me a scale. Now, how to figure out what scale to use? Look at the size of the answer sheet that is given to you. Alright, if I have this amount of space, you roughly estimate I need to draw 25 newtons. You look at the space you have, you know you need to draw a parallelogram of 5 cm, 25 to represent 25 newtons each. So I would say if I were to choose a scale of 1 cm is to 1 newton, then I need to draw a line that is 25 cm, which cannot fit here lah. So I decide to go with a scale of 1 cm is to 5 newtons. Then I think the answer will fit nicely lah. So step 1, decide on your scale. So I've drawn the scale. I decided on 1 cm is to 5 newton. Step 2, indicate a point as the object. And how do you indicate a point? Just use a dot. Alright. After which, you draw all the forces acting from the object, just like how you deal with free body diagram. Draw forces acting from the object. Make sure that the angle is correct, and make sure that it's correct to scale that you have selected. So remember this, I have a picture. F1 40 degrees from the horizontal acting this way, 25 newtons, 40 degrees F2 in this direction. Alright, so again, I will just do steps 2 and 3. Easiest way is for me to indicate using a dot. So I say this is the object. Alright, the next one is to draw all the forces acting from the object. Now, the forces acting from the object are 40 degrees in this direction and 40 degrees in this direction. So you remember, you need to play around a little bit with how or when the forces are drawn. So 40 degrees here and 40 degrees in here. Alright, so I can just shift them around whenever I need. So I want to draw it acting from the object, so I shift this and I move it over here. So this is actually force 2 and this is force 1. So this is force 2, this is force 1. So to make my life easier, I draw a horizontal line first so that I can then use it to take reference and draw 40 degrees. So I draw my horizontal line. Alright, use a protractor. Because I know the forces are 40 degrees, I just mark 40 degrees here. And I mark 40 degrees here. Alright, so now I got the 2 points. I know the line must be 5 cm long. Alright, so just find the line, connect from here. I need basically draw a 5 cm line acting in this direction. So I just draw. And I label this as 40 degrees. And this is force F2. Alright, so I'll do the same with F1. I need to draw a 5 cm line acting in this direction. 5 cm. Draw. F1. This is 40 degrees. So what you need to do essentially is to head to tail this fella. So I need to make the tail of this fella. I need to shift it all the way up until here. Then the resultant is from the start point to where my final end point is. Parallelogram is just doing head to tail 2 times for both sides. So do the head to tail first here and do the head to tail over there. Alright, the parallelogram makes your life a little bit easier because you know certain properties of parallelogram. If this is 40, this is 40, that means this is 100 degrees. And if I were to draw a parallelogram, then if I were to pull this fella here, make sure I retain the line and transfer it over here to form a parallelogram. I know that the interior sum of these 2 angles must be 180. So I know that this is 80 degrees. So that's why parallelogram is a little bit easier to work with. So I measure here, it should be 80 degrees. Then basically what I need to do is transfer this line over here. Oh no, I got so many dots. So I need to figure out which one. Give me a second. Okay, this one, 80 degrees. Now, in transferring this line over, this vector doesn't really exist because this vector is already drawn over here. So, since it is a working line, you are expected to draw it as a dotted line. This is 80 degrees and this is a 5 cm line. Now, of course, you can do again 80 degrees and then measure, make sure this is 5 cm and then draw a 5 cm line. But if you have drawn this line correctly, all you need to do is to connect this and the parallelogram is now formed. Of course, this you cannot draw it like this. It must be dotted line. Alright, and the resultant is therefore from here to here. Again, start to the end, and I represent with double arrowhead. You must draw double arrowhead. Now that I've got this, let's look at steps 4 and 5. Just quickly, use the 2 forces as vertexes of parallelogram and form a parallelogram. Take note that the consecutive interior angles are equal to 180 degrees, which means this plus this must be 180. This plus this must also be 180. So therefore, this is 80 degrees. Alright, then step 5, you are supposed to draw a resultant force. Make sure that you indicate with a double arrowhead to show the resultant force. Now, the last step, step 6 and 7, is to measure the resultant and state the resultant corrected to the scale. And then some questions may ask you to describe the direction of the resultant. So I'll show you how to do that as well. So now that I have the resultant, all I need to do is to put my ruler here and measure. My resultant is about 6.4. So 6.4 cm corrected to the scale of 1 cm is to 5 Newton. So my resultant force is actually 6.4 cm times 5. And the answer is 32 newtons. So I know that the end effect of these 2 forces of the string is 32 newtons. And to give a perfect descriptor of the direction, you give it with reference to one of the original 2 vectors. It doesn't matter which one. You either give me this one or you give me this one. So if I have to take my protractor and measure, I get that the angle is 50 degrees. So if this is 50 degrees, this should also be 50 degrees because I know this is 100. So you can give from either one. So you can say the resultant is 50 degrees from F1. Now, this is also not fully sufficient. 50 degrees from F1 means it could be in this direction. or also in this direction 50 degrees. So you must tell me this direction. So this direction is anti-clockwise direction. Or the other way is you can tell me is resultant is 50 degrees clockwise from F2. Because from F2, I rotate 50 degrees clockwise in this direction, I get the resultant force. So this is how the parallelogram method works. Now the power of this, again as I mentioned, now that I know the resultant of these two forces, which is like this, I also know what is the third force. Because this resultant force and this one must balance out each other. And they must cancel out, and the direction is exactly opposite to that. Alright, so let's discuss head to tail now. Alright, so I'll go a little bit faster for head to tail because I think you roughly know. The steps are pretty much the same. You select the proper scale based on the size of the answer sheet that you have. You indicate a point as an object using just a dot. Then you draw, in this case it's slightly different. You only draw one of the forces. In the parallelogram method, you draw all the forces acting from the object. Alright, the other step is to then draw the second force. So I'll write this all down first so that you all can have a look at the thing and copy down. Alright, finally draw resultant force. Everything else after that remains the same. Use a double arrowhead, measure resultant, corrected to scale, that means the magnitude. And then you must tell me the direction as well. Alright, so when do I use head to tail? Just now we use parallelogram when I have the object and the forces are already drawn in this manner, meaning that all the forces are drawn as acting from the object in a certain direction. That means the tail and the tail meet. Now, sometimes it may be easier for you to use head to tail when they give you a situation like this. They say that an object is moving forward or upwards is 5 meters per second. Let's say it's a boat. A boat is moving upwards or north with a speed of 5 meters per second. Alright, at the same time there's a current pushing down with a rate of 10 meters per second. So they will ask you where will the boat go, in which direction, at what speed. So when it's not given like this, it means they give you as two different vectors, not linked to the object or not drawn as from the object, then it may be easier for you to use head to tail. So let me illustrate how to do head to tail. Again, since we already decided on the scale just now, and the paper size is the same, and our answer should also be the same. You draw a dot to indicate the object, draw a horizontal line to make your life easier. Alright, so now your role is to draw, instead of drawing both forces, you are supposed to only draw one of the forces, this one. Draw one of the forces from the object. So make sure that you retain the correct size and the correct angle. So let's say, if you can recall, there are two forces, 40 degrees. This is force F1, 40 degrees. This is force F2. Let's say I go and decide to draw force F1 first. So F1 is 40 degrees from the horizontal upwards. So I measure 40 degrees. I put a mark here. Alright, and then this is supposed to be 5 cm long. So I measure 5 cm. Okay, sorry, the camera was being weird. So I measure 5 cm and I draw the line from here to here. So now I have drawn force F1 and this angle is 40 degrees. Now head to tail, meaning I need to draw F2 in the correct direction. The tail end will start at where F1 head is. So head to tail. So this is where it is a little bit difficult because you need to figure out what is this angle here. So it might be slightly challenging. So if you are good with angles, then no problem. You can just carry on and figure it out. For those of you who struggle, I draw another horizontal line. If this is 40 degrees, your alternate angles, then by default this is also 40 degrees. So now I have the horizontal line. I know F2 is supposed to be 40 degrees above the horizontal line, so it must be somewhere like this, and it's 40 degrees. So I know the angle that I need to measure here in total is 80 degrees. So Then all I need to do, put over here, put a mark on 80 degrees, and I know F2, I'm now drawing F2, here this F2, and I know it's also supposed to be 5 cm. So just need to put the ruler here, make sure it's 5 cm, just draw. Now that I've drawn this, represent with the arrowhead, all I need to do then is to connect the start to the end, double arrowhead, to show my resultant. So there you have it. If you measure this, the answer should be exactly the same. 6.4 cm again, as you can see. So remember to correct your answer corrected to the scale. So the resultant is 6.4 cm times 5. The answer is 32 newtons. If you measure this, you can either measure this angle or this angle. Either way will do, because this resultant force, to get this resultant force, I need to rotate F1 in this direction. F1 in this direction to get this. So if I measure this angle, there you have it. The angle is about 50 degrees. If I want to measure from F2 as well, also no problem. So I just measure this angle. There you go, 50 degrees as well. So to get this resultant vector, I need to rotate F2 in this direction by 50 degrees, then I will get. So the answers all are still the same. So the direction is 50 degrees. If you look here, this is in the clockwise direction, clockwise from F2, or 50 degrees this direction, anti-clockwise from F1. Now, some of you may be wondering, can I draw F2 first? Sure, you can. Just draw F. You can also start off with F2, end up with this. Then again, do your whatever reasoning. You know this must be 80 degrees. Then you draw F1 in this direction, and then you will get the same answer, exactly the same. Alright. So my recommendation, if you can, please use parallelogram, because most students tend to make less mistakes using the parallelogram method. Alright, now guys, if you flip over to the very last page of your notes, I just want to highlight, this is a sample O-level question, and I want to highlight some differences between combined and pure science, pure physics students. The pure physics, what is expected of you is what we did just now with the head to tail method and just drawing all the way from the start. But for combined science students, we just take note that sometimes they may make it a little bit easier for you. So either there are quite a few things for you to deal with: scale, the direction must be correct. So sometimes the O-level question will be set in such a way that they will give you one of those information, or in fact they may give you both. So for this example here, taken from the 2018 paper, they actually gave you both the scale and have already drawn the first two vectors for you already with the correct angle. So that means if you look at it, they give you a scale of 1 cm to 10 newtons, and they say this is 60 newtons and this is 70 newtons. So if you put your ruler here, you measure, it's exactly 6 cm. So they have already settled the scale for you and the direction of the vectors. So there's no need for you to deal with it too much. You just need to complete your parallelogram in this way, because the tail and the tail is meeting at this point here. Now, there are some years where they only give you the correct direction, meaning the angle, but they give you a very long line, like so, and then they ask you to kind of figure out your own scale. Now, I have had many students who have taken the fact that they have drawn this line and have used the whole entire length. So let's say I've drawn an 8 cm, what was given is an 8 cm line. They try to fit the 8 cm line into a 60 newton, and then they end up with an odd scale, and they cannot get the answer. So when they don't give you the scale and they give you just a line like that all the way, you are supposed to figure out your own scale. Let's say you pick the scale 1 cm is to 10 newton, then you mark a point here. So this is where the end of your vector is. So 70 newton, you measure 1 cm to 10, you measure 7 cm, you mark an end here. So then you just, they want to test you on your scale, so make sure that you do this correctly. So let's just solve this question that was given to us with the scale already settled and also the direction already drawn in for you. So I see that the direction, this angle here is 140 degrees. So I know this is 140 degrees. They're asking me to find the resultant of these two vectors. So all I need to do is complete the parallelogram with these two as the vertexes. If this is 140, that means the angle here must be 40 degrees. So put here 40 degrees. This line is supposed to be 7 cm because it's 70 Newton. I just need to transfer it over here. Now, in the O levels, they will give you the question properly. And I think in this case, the printing squeezed the answer. So my answer may look like it's cutting into the question. But if your answer cuts into the question during O level, please make sure you redo, because then that's actually wrong. So 7 cm long. Make sure that this line is a dotted line because the vector has already been drawn for you. If you draw this accurately, there's no even real need to measure another 40 degrees here and draw 6 cm. We just need to connect these two. And the resultant is the start to the end point. Draw. Measure the length of this one. This one must be corrected to the scale. So I got about 44.5. So the answer is just 45 newtons. Because this is 45 newtons, then this is the resultant of these two vectors. This and this must be exactly equal and opposite in direction. So the question is solved. Now there are a few other questions that are quite often, appear quite often in the O's, where they tell you I have a stationary object, I got three forces F1, F2, F3. Please draw the vector diagram of this. If it's stationary, then you know F1 plus F2 plus F3 must equals to 0 newtons, the resultant. Because only when you have 0 resultant force can my object remain stationary. So basically what you're looking is for a triangle with 3 vectors drawn that will start at one point and then end at the exact same point. Then that will indicate as 0 newtons. So you are looking for something with F2, F3 and F1 like that. Alright, sometimes they may try to trick you, they may draw things like that, the arrow is in different direction. Just take note that one of the unique things is that whenever 3 vectors form a closed loop, because they connect from here to here to here, this is a closed loop system, then the resultant force is 0 because it ends back at the start point. Another one type of question that is common. I have 2 vectors here. Find the resultant. They will ask what is not the possible value of the resultant if my angle can vary from 0 to 180 degrees. So just take note if the angle of incidence is 0, that means 3 Newton and 5 Newtons are pointing in the same direction. So 8 Newton is possible. Alright. 7 and 2 is also possible depending on the angle. The only one that is not possible is A, 1 Newton. Because even if the angle is 180 degrees, which means basically is 5 Newtons and 3 Newtons in this direction, and the angle theta here is 180 degrees, then even if it's 5 and 3, the very minimum that it can go down to is 2 Newtons. So 1 Newton is not possible. So these are the type of the questions that will appear. Alright. I think I missed this last slide. Some of you may be asking, so I just leave this here. But through the course of our discussion, you should already know the answers and be able to fill in the blanks. Alright, you can do up the rest of the questions. If you have any questions, don't hesitate to contact me via email or the usual means. Alright, thank you. Bye bye.